Nestled in the picturesque city of Geneva, Switzerland, the European Organization for Nuclear Research, commonly known as CERN, stands as a beacon of scientific exploration and discovery. At the heart of CERN's mission lies the quest to understand the fundamental building blocks of matter, ranging from the smallest particles to the vast reaches of the cosmos. One of the most remarkable scientific endeavors here revolves around the fascinating tale of the antimatter factory, where visionary scientists are pushing the boundaries of human knowledge and technological ingenuity. Antimatter, as we know, is central to one of the greatest mysteries of our universe. Why does the universe even exist? Understanding antimatter is crucial to unraveling the fundamental truths of our existence. However, in the pursuit of this profound enigma, CERN has encountered an unexpected phenomenon involving antimatter, one that no one can yet explain. This discovery has led to a perplexing puzzle that continues to baffle researchers. So, what exactly did CERN find that has the scientific community so confounded? Antimatter may sound like something out of science fiction, a material that mirrors regular matter but would release an immense amount of energy upon contact, equivalent to a nuclear bomb. No wonder the physicist who first predicted the existence of antimatter was wary of what he had uncovered. Today, physicists use massive particle detectors to examine subtle effects in the hope of shedding light on the elusive nature of antimatter. Where has all the antimatter gone? This question is tied to the very first moments of the Big Bang, almost 14 billion years ago. Something happened in those early moments that transformed a universe filled equally with matter and antimatter into one that seems to lack antimatter altogether. Did antimatter vanish due to some peculiar anomaly in the laws of nature? Or is it still out there, perhaps lurking in anti-galaxies orbiting antimatter stars? One thing is certain: antimatter is very real. The first hints of antimatter emerged in 1928 when British physicist Paul Dirac, at the age of 26, introduced an equation that unified at least three key theories in physics: quantum mechanics, electromagnetism, and Einstein's theory of relativity. Dirac's equation had not one, but two solutions. One described the properties of the electron, while the other predicted the existence of a mirror particle with the same mass but opposite charge, the positron. In 1932, physicist Carl Anderson's discovery of the positron confirmed Dirac's prediction, offering a glimpse into the mysterious world of antimatter. While electrons are everywhere, detecting even a single positron required sophisticated particle detectors. Yet, there was no explanation in Dirac's equation or the known laws of physics for why the universe should favor matter over antimatter. One possibility was that Earth might simply lie in an antimatter-free region of the universe, with entire stars made of antimatter hidden somewhere out there. If that were the case, it would be easy to spot because when antimatter meets matter, they annihilate each other in a tremendous burst of energy. Einstein's famous equation, E=mc², shows that even a tiny amount of antimatter would release an extraordinary amount of energy, comparable to a nuclear explosion. The annihilation of matter and antimatter is the most powerful energy source in the universe, and its effects are hard to miss. So, if antimatter stars or anti-galaxies exist beyond our own, Earth should be bathed in a constant glow of gamma radiation, a sign of the destruction of matter and antimatter. However, the truth is strikingly different. Since the 1960s, astrophysicists have sent increasingly advanced gamma-ray detectors above Earth's protective atmosphere, trying to detect signs of antimatter. The results have been consistent. There are no signs of antimatter objects anywhere in the universe. The absence of gamma rays from our own galaxy suggests that the nearest antimatter star is at least 10 light-years away, with no more than 1 in 10,000 stars made entirely of antimatter. On a larger scale, the lack of antimatter is even more striking. The gamma rays coming from distant galaxies suggest that only about 1 in 100,000 parts of extragalactic matter might consist of antimatter. So why is there more matter than antimatter? Something must have happened during the Big Bang to eliminate antimatter, while leaving enough regular matter to form galaxies, stars, and life as we know it. In 1964, American physicists studying kaon mesons discovered a strange phenomenon known as charge parity, CP violation. This indicated that antimatter doesn't always perfectly mirror the properties of regular matter. The amount of CP violation observed was small, but in 1967, brilliant Soviet physicist Andrei Sakharov proposed that this could explain why the matter created in the Big Bang didn't completely annihilate with antimatter, leaving behind the dominance of matter in the universe. Two major questions arose from Sakharov's hypothesis. First, for CP violation to explain the dominance of matter over antimatter, it must apply to more than just kaon mesons. Second, even if CP violation applies to all particles, the effect must be strong enough to account for the overwhelming prevalence of matter in the universe. These questions are now being tested in massive particle detectors attempting to recreate conditions from the early universe. At Stanford University in California, the 1,200-ton Bobber particle detector is being used to study the effects of colliding electrons and positrons with a force never before seen, replicating conditions just moments after the Big Bang. The resulting unstable particles, called B mesons and their antimatter counterparts, can be studied for signs of CP violation. In 2001, scientists working at Bobber, as well as at a similar facility in Japan called Bell, announced that they had successfully detected CP violation between B mesons and their antiparticles. This confirmed that CP violation is not limited to one type of particle. Moreover, the observed level of CP violation was consistent with theoretical calculations based on the so-called Standard Model, which is the most widely accepted theory for understanding subatomic particles. However, the level of CP violation was far below what would be required to explain the overwhelming dominance of matter over antimatter in the universe. Physicists see this as evidence that the Standard Model is incomplete, lacking some crucial element. What exactly that element is remains unclear, but experiments are underway to uncover it. Astronomy and particle physics are often dismissed as irrelevant to everyday life, but by investigating how antimatter lost out to regular matter during the birth of the universe, scientists are working to uncover the secrets of our very existence. This is why physicists at CERN are committed to exploring the mysteries of antimatter, as it holds the key to understanding the fundamental nature of the universe and our place within it. Antimatter and its properties have long been a fascinating yet mysterious area of study in physics. The primary question surrounding antimatter is whether it reacts to gravity in the same way as regular matter. Although antimatter and matter are thought to behave similarly under the influence of gravity, direct observations of antimatter falling freely under Earth's gravitational pull have not yet been made. This is primarily due to the difficulty in producing and containing antimatter, as it annihilates upon contact with regular matter. Over the past 2 decades, researchers at CERN, the European Organization for Nuclear Research, have been producing antimatter by using high-energy particle collisions. The process involves slowing down antiprotons, produced from particle collisions in CERN's proton synchrotron, from nearly the speed of light to speeds of just a few hundred feet per second, cooling them to about 15 degrees above absolute zero. These antiprotons are then combined with positrons, the antimatter counterpart of electrons, produced from the decay of radioactive sodium. The combination forms antihydrogen, a simple antimatter atom consisting of an antiproton and a positron. In 2002, researchers led by Dr. H observed that antihydrogen emitted light at the same frequencies and wavelengths as ordinary hydrogen, which confirmed that antimatter behaves similarly to regular matter in this respect. Since then, many indirect experiments have suggested that antimatter might also fall in the same way as matter under the influence of gravity. However, these experiments have not been conclusive due to the overwhelming strength of electromagnetic fields used to control antimatter, which can obscure the effects of gravity. In recent experiments, antihydrogen atoms were contained within a metal chamber, held in place by magnetic fields. These fields prevent the antimatter from coming into contact with the walls of the container, where it would annihilate upon contact with matter. The researchers cooled the container and its antimatter to near absolute zero, draining energy and slowing the particles down. When the magnetic field was switched off, the antihydrogen atoms were released and observed to fall under the influence of gravity. The results of this experiment surprised the team. Antimatter appeared to fall at the same rate as regular matter. Dr. Farr, the lead physicist, expressed amazement at the outcome, stating that no one had expected antimatter to behave in such a way. The findings do not, however, conclusively prove that antimatter behaves exactly the same as matter in all circumstances, nor do they resolve the greater mystery of why the universe is made predominantly of matter. What makes antimatter so intriguing is the fact that it mirrors regular matter in many ways, yet remains deeply mysterious. Its existence and the imbalance between matter and antimatter in the universe remain unsolved puzzles. Theoretical physicist Paul Dirac predicted antimatter in 1928, when he realized that equations describing electrons also suggested the existence of particles with the same mass but opposite charge. These particles, called positrons, were discovered in 1932. According to the Big Bang theory of the universe's origin, the universe should have produced equal amounts of matter and antimatter. However, what we observe today is a universe made almost entirely of matter, with very little antimatter. This discrepancy remains one of the biggest mysteries in modern physics. At CERN, antimatter is created in particle colliders, such as the Large Hadron Collider (LHC), through high-energy collisions. Once antiprotons are produced, they need to be slowed down, which is accomplished through a series of decelerators. After slowing down, these antiprotons are combined with positrons to form antihydrogen, which is then contained in a magnetic trap to prevent it from coming into contact with regular matter, which would result in annihilation. One of the major ongoing questions in antimatter research is how gravity affects it. Researchers are testing whether antimatter and matter fall at the same rate. Early results from the alpha experiment suggest that antimatter does fall in the same way as regular matter, but further research is necessary to confirm these findings. Another important area of research involves CP violation, which refers to the differences in how the laws of physics apply to particles and antiparticles. Understanding CP violation could help explain why the universe is dominated by matter, as this could lead to a better understanding of the imbalance between matter and antimatter. The study of antimatter is crucial for answering some of the most fundamental questions about the universe's origin and the nature of the laws of physics. Advances in antimatter research could also have significant technological implications, potentially enabling breakthroughs in energy production and space travel. In conclusion, while significant progress has been made in the study of antimatter, many questions remain unanswered. The work being done at CERN and other research facilities continues to push the boundaries of our understanding of the universe and could lead to new discoveries that reshape our understanding of the fundamental laws of physics.